Okay, so question 27.2. It's kind of an interesting question. This is sodium polyacrylate. This compound here is a synthetic polymer used in diapers because of its ability to absorb several hundred times its own mass in water. Now you know. This extraordinary polymer is made from another polymer. So it's made from the saponification of polymethyl acrylate, which is this polymer here, via hydrolysis of the ester groups. But again, it's a basic hydrolysis, so it's saponification. Draw and name the monomer used to make polymethyl acrylate. So it's just asking us to name and draw the monomer that polymethyl acrylate is made from. So we would just put a double bond between the two carbons, and one side has two hydrogens, and the other side has the methyl ester. And we have the proton here. So we just get rid of the poly, and the name of this compound is methyl acrylate. There we go. Methyl acrylate is the compound. Give me a thumbs up if you think you could do that. Yep. Polymethyl acrylate. I just get rid of the word poly. Perfect. All right. Awesome. So there you go. So that's a little bit about nomenclature. Now, in terms of classes of polymers, the way you can put them together, there's a few ways you can do it. And the simplest of all, and again, I shudder to use the word simple, but it fits here. The simplest type of polymer you can have is a homopolymer. And that's a polymer where all the repeating units are constructed from one type of monomer. So we've already seen a bunch of those this morning. So things like Teflon, polyethylene, what else? I don't know, styrene is another one that we saw. We'll just put here, etc. So those are homopolymers just made from one type of polymer. Another polymer that's even cooler is, if you ask me, is a copolymer, because it takes some experimentation to put these things together. For example, I know you've all heard of saran wrap, okay, some kind of cruel joke perpetuated upon society. But saran is actually a copolymer. It's made from vinyl chloride, which is this compound, and vinylidene chloride, which is this compound. So you can see that they kind of alternate here, A, B, back and forth like that. And we're going to talk about alternating copolymers and random copolymers in a minute. But saran is made from both of those monomers put together. And what's cool about these, why I think copolymers are so neat, is because they have completely different properties than the homopolymers that they're made from, right? So you think about polyvinyl chloride, which is like a really hard, brittle plastic almost, versus saran wrap. I mean, it's completely different. So it's pretty cool how they can experiment with different monomers, put them together in different ways, and make new neat materials that way. So here are some polymers or copolymers rather, that you would know. I think everybody who's hearing the sound of my voice is going to recognize saran, right? Which is found in saran wrap or any kind of plastic wrap, which again is made from vinyl chloride and vinylidene chloride. Then the next one is SAN or SAN. And SAN is, and you can see it comes from styrene and acrylonitrile, right? SAN, get it, right? Anyhow, so SAN, it says is found in things like battery cases. So if you think about, like, maybe if you have a boat or something and then you put a battery inside of it, or dishwasher safe kitchenware. So that's things like just cheap plastic that you buy that you can put in the microwave, like Tupperware and things like that. Okay. The next one is ABS plastic, and ABS, so that stands for acrylonitrile butadiene and styrene. So ABS, they put them all together. And I'm sure a lot of you have heard of ABS bumpers, right? So your bumper is made of ABS plastic, still cracks after it's been touched, like a collision at 1 mile per hour causes permanent damage or something. And yeah, crash helmets, luggage. So I guess if you see, that fancy, I don't know, Samsonite luggage or something, it's probably made out of ABS. What else? Butyl rubber. I brought that up earlier on when we talked about isobutylene. So polyisobutylene is found in caulking and sealants. But if you take isobutylene and mix it with isoprene, and isoprene is actually a pretty neat compound, which we don't talk about in this class. But if you want to do a Google search on isoprene, I don't know, you can do it in your own spare time, but you could Google isoprene. It's a pretty interesting compound. It's a building block of a lot of biological molecules. But anyhow, you mix those together, you get butyl rubber, and that's found in all kinds of tubes and balls, things. It says they're sporting goods. And the last one that I think is the last one they put in here for the copolymers is Viton. And Viton is made from vinylidene fluoride and hexafluoropropylene. And honestly, you guys, I wouldn't have known really what Viton is until I started working as a chemist. I'd never, I guess if I had done more automotive work, maybe I would know about Viton. But when it says gaskets and seals, so Viton, it's a type of rubber that is very, very strong. I mean, it's very resistant. It's resistant to strong acids and strong bases. So that's how I know it, is because it's so tough around acids and bases, and I worked with them every day as a bench chemist in industry. So Viton, very cool compound, and yeah, it says here it's also used in the automotive industry. Now, do you have to memorize all of these? No, you don't have to memorize all of these different copolymers and what they're made from exactly. But you should have an idea that when you put different monomers together, you get copolymers, and you get completely different properties than the monomers have themselves. Now, in terms of copolymers, how do they go together? There's a few ways they can go together. Okay, one thing is to have a random copolymer, and you can see where that's coming from. It's just your monomers are just mixed in random order. Okay, just there's no order to anything shown here. Whereas an alternating copolymer, you can see that it's very sanitized. It goes A, B, A, B, A, B. And even your textbook says that, you know, even if you have an alternating copolymer, there's still going to be random portions in it, okay? But it will maintain the properties of the alternating copolymer. Then we have a block copolymer. Block copolymers are where you have like one, it's almost like an oligo, what we call an oligomer, and that's where you have a few subunits put together, and then you bind to another group of subunits. That's a block copolymer. And a graft copolymer, you could probably figure that out without my help, is that you have the main chain, and then you have branches grafted onto it that are different. Okay, so those are the main types of copolymers that we can have. Okay, so in terms of a copolymer question, the kind of thing you would be expected to know, it says, draw a region of an alternating copolymer that's made from ethylene and styrene. So you guys all know what the structure of styrene is. If I just pencil it in here quickly. So this is styrene, and then this is ethylene. And if I put the two together, I'm going to get some kind of alternating copolymer. You know what I'll do is maybe I'll color code it. And I'm sure you guys don't need my help with this. But anyhow, so if we were going to draw a region, so let's start with styrene since they put that first. Now you can start by writing CH2 like that, or you could condense it just to make it a little faster and say CH2. Then we have our methine with our phenyl attached to it. So there's styrene, and now we're going to have an ethylene, and now we're going to have another styrene, and now we'll do one more ethylene like this, and then we'll just close off the whole thing. So we'll say N and N like that. So there you go. There's repeating, and that's an alternating copolymer. You see it goes A, B, right? That's what we would draw for an alternating copolymer. Everybody, give me a thumbs up if you follow me on that one. Drawing an alternating copolymer back and forth and back and forth. Cool. It's not quite as complex as something like Michael addition, huh? Anyhow, so let's move on. It says draw a region of a block copolymer. So let's just try this. It's made from propylene. So propylene is this compound, and vinyl chloride, which is this compound. So why don't we do like, we'll do like A, and then we'll do B, something along those lines. Okay, so we'll start out with our propylene. So we've got CH2, CH3, CH2. And again, if you did it with 2, that's totally fine. I'm doing 3 in a row here. It doesn't ask us for anything specific. It's just saying, show me what a block copolymer is. So now we're going to do our vinyl chloride. So CH2, CHCl, CH2, CH, Cl, CH2, CH, and Cl, and there we go. Maybe not my neatest work, but you get the idea of our block copolymer. There we go. So again, if you put 3 or 4 of them in a row, doesn't matter. I just chose 3 and 3 arbitrarily. Okay, just pulled that out of thin air. Okay, I get another one in here. Let's try another one. So it says here, identify the monomers that would be used to make this copolymer. So you can see there's two monomers here. There's this first one, and then there's a second one right next to it here. So the first one is going to come from this compound, and the second one is going to come from this compound. And I'm sure you all recognize these two compounds. The one on the left, that's isobutylene, and the one on the right, that's styrene. All right, there we go. So there's a copolymer. We just identified a couple of monomers that it's made from. Okay, so if we turn our attention to the next section, so 27.4, it says here that polymers can be classified a number of ways. The first one is type of reaction. That's covered actually in 27.4, and we're going to go over that in detail. Mode of assembly, that's covered in section 27.5. Structure, that's covered in section 27.6. And then finally, properties is covered in section 27.7. We are actually going to skip all of these parts here. So I'm going to put here, skip to Maloo. We'll just skip those parts. And the reason why is they're not covered in the final exam. I don't think I've ever seen a question about those in a DAT or an MCAT or anything like that, so I wouldn't stress about that. But we are going to talk about the type of reaction. That is important. I will just go out on a limb and say that most of the polymer questions that you would see on any kind of standardized exam in chemistry, we've covered it already today. I mean it. We've covered the content already. But you should know the types of reactions that put polymers together. So there's three that we're interested in terms of addition, okay? We're going to talk about radical addition. Okay, when we're talking about addition polymers, we're going to talk about radical addition, we're going to talk about cationic addition, and then we're going to talk about anionic addition. So you have to know all three of these different types of addition polymers and the mechanism for how they go together. But before you stress, okay, the mechanisms are no more complex than anything you've ever seen in this class. So it's very, very doable. And it says here that free radical addition occurs through a chain reaction. Well, let's check this out. So we're starting with free radicals. So we're starting with radical addition. What color did I use? I used blue for radical. So we're starting out with the radical addition. And you guys remember initiation, propagation, and termination very well, I'm sure. And so how do you initiate the growth or the formation of a radical addition polymer? Well, the way we do it is we start it with some kind of peroxide. And if you're thinking, well, hey, I recognize that from my anti-Markovnikov addition of HBr across the double bond, it's the same kind of peroxide, right? You heat that up to maybe not all that hot. I mean, maybe only around 80 degrees Celsius, and it's going to break apart to give you a pair of radicals. So then the radical is going to react with your monomer, and then you end up with a combination of the two, but you've got a radical. So now what does that mean? It means that once that radical sees another monomer, you're going to get an addition reaction, right? And you should be able to draw, I'm going to put a red star on this, you should be able to draw the curved arrows, the fishhook arrows here, right? You see that you're forming a sigma bond right here, and that you're breaking this pi bond and making a new radical over here. So you're just going to keep putting in the monomer over and over and over. And there you go. So that's what we call a chain growth polymer, right? You keep adding something to the end of the chain, and the chain gets bigger and bigger and bigger. So that's the propagation step. So we've covered initiation and propagation. Well, what's termination? If you remember from way back in chapter 10, termination is anytime two radicals come together to make a non-radical. So you could pick any two radicals you want, okay? As long as it's adding to the end of the chain and another radical. So it could be the oxygen radical here, or it could be two ends of a chain coming together, and you annihilate the radicals, and there you go. So that is radical addition, okay? And it's initiated by a radical species. So there you go. So radical addition, done with radical addition. Now, what about cationic polymerization? So we've covered radical. We've covered just radical. So cationic, I think I used the red color for that one. I think I used green for the anionic. Anyhow, so cationic addition polymers are a little bit different in that it works better when you have some kind of ethylene derivative that possesses an electron donating group, okay? And you guys remember what an electron donating group is. We talked about those quite a bit. It's something that's going to donate electron density, right? Oops, like this and like this, okay? Now, if you look at the methyl group, we know that a methyl is electron donating via hyperconjugation. And you might think of this oxygen and say, well, wait a second. I thought that oxygen was the second most electronegative element in the whole periodic table. Shouldn't that be electron withdrawing? It is electron withdrawing by induction, but by resonance, it's actually electron donating. Okay, so resonance, if you remember aereo, resonance beats out induction, right? It comes first. And the same thing would apply to this amine here. Okay, yes, nitrogen is an electron withdrawing element in terms of its electronegativity, but it's also electron donating in this case. And so all three of these groups, the alkyl group, the methoxy group, or the alkoxy group, whatever, the amino groups, they're all going to be electron donating. And so if we underline here, electron donating groups, okay, E, D, G's, they're going to help stabilize a cation. Let's think about that. If you had a cation, you know, if you have your R group over here, and then let's imagine you have the methoxy group here, and then you have a cation, well, the methoxy group can donate electron density by resonance and stabilize that cation. So we're still going to have the same old initiation, propagation, and termination step for cationic polymerization, but this reaction is going to be initiated by an acid. So we're going to take our polymer and we're going to treat it with an acid, and then you're going to do an addition to the pi bond, and then we end up with a carbocation. And what's going to happen with that carbocation is that carbocation is going to react with another monomer like this. So now the monomer, right, the pi bond is going to act as a nucleophile. It's going to attack the carbocation, but now you make a new carbocation, and it keeps going and going and going. Okay, it says here, the pi bond of the monomer acts as a nucleophile. It attacks the carbocation, and it keeps building up the chain. So then how do you terminate the whole dang thing? Well, you could either throw in a base that could do an elimination reaction, as is shown here. So you do an elimination, and that shuts it off. Or you could add some kind of nucleophile. You could throw a nucleophile in there, and that's going to neutralize the carbocation. And there you go. So that's initiation and propagation for cationic polymerization. But remember, you want to have an electron donating group for cationic polymerization. All right. Now, a little bit more about cationic polymerization. It says here, initiated by acid. And I had actually made a note here at one point that the acid, I'm not going to ask you about this because there's a whole holy host of acids that could be used to promote the addition, cationic addition process. But sometimes we make the acid from a mixture of boron trifluoride. So we mix boron trifluoride with water, and then we end up with this Zwitter ion. So if I can draw the whole thing here that looks like this, you have a positive charge here, and then you have a negative charge on your boron like that. So that is the acid that oftentimes is used to initiate the reaction, but it's just kind of something I wanted to show you once. Now, in terms of, you know, monomers that will work well in cationic polymerization, you can imagine that isobutylene is going to work really, really well. Why? Because you end up with a tertiary carbocation after your first proton transfer. And so this carbocation is really stable. And so something like isobutylene is very prone to cationic polymerization. Whereas something like ethylene, cationic polymerization doesn't even happen with ethylene. Now, if you're saying, well, why not? It can't happen, right? Because you end up with a primary carbocation, and that is a huge no-no in organic chemistry. It's so unstable, it just doesn't happen. And so since it doesn't happen, it doesn't happen. That's like a debate-worthy performance there. Anyhow, now in terms of anionic polymerization, all right, anionic polymerization, we're going to look at the opposite of cationic polymerization. We're going to be making anions along the way. And so we're going to want to have electron withdrawing groups like a nitrile or some kind of carbonyl like an aldehyde or a ketone or an ester, something like that. These are electron withdrawing groups. Okay, why are they so great? Because if you form an anion, make that a little bit cleaner, but let's just say you made an anion here, and then you have an electron withdrawing group, okay? If you have an anion here, right, that of course is resonance stabilized, okay? And if it's resonance stabilized, well, that means it's going to be more prone to work in an anionic polymerization. So it's the same all three steps. We have our initiation, propagation, and termination. So what initiates the anionic polymerization reaction? It's going to be the reaction of a strong nucleophile or base like butyllithium. So you guys remember the butyllithium um, compound or base, okay, which is also a nucleophile. So this is butyllithium. So the butyl carbanion is going to act as a nucleophile. It attacks the monomer. Then you end up with an anion or a carbanion. But remember, you've got an electron withdrawing group here pulling electron density away, which serves to stabilize that negative charge. And so now that you've got the negative charge on there, you just keep adding the monomer and adding the monomer and adding the monomer, and it grows over and over and over like that. And so yeah, so sometimes we call this a living polymer. I don't know if you've ever heard this expression before, but we'll put here living polymer, because the idea is this with anionic polymerization, that when you have that negative charge, it'll just kind of hang out there, and then you can just keep throwing more monomers in. It gets bigger and bigger and bigger, and so that's why we call it a living polymer. Anyhow, in order to stop the reaction, you can quench it with water. Okay, so just throw some water in and do a proton transfer, or you could throw in an electrophile like CO2. You know, students always get annoyed at this. They're like, well, there's a negative charge. Isn't it going to keep going? Remember, the negative charge on a carboxylate is going to be very stable, right? Because it has two resonance forms, and so it's not going to serve as a very good nucleophile. And you could also do a proton transfer. You could put aqueous acid in or something at the end, and then you would end up with CO2H. Okay, so don't stress about that negative charge at the end. So again, if you're astute, and I know you all are, you probably noticed that anionic polymerization is kind of like a Michael reaction. Okay, so anionic polymerization, it's like a Michael reaction. Okay, you have your Michael donor and then the double bond here, so that's your Michael acceptor. Okay, and again, the electron withdrawing group is what stabilizes the carbanion, the anionic intermediate, and then you keep going and going and going, and you have your, again, this is your living polymer, so to speak, is there. So there you go, a little bit about anionic addition polymers. Now, there are some other types of polymers. For example, a condensation polymer. You guys all know this reaction is near and dear to everybody's heart. How about this one? The Fischer esterification. You're like, yes, Mr. Dion, I take a carboxylic acid, an alcohol, catalytic amount of acid, remove water, and that's a beautiful way to make an ester, the Fischer esterification. If you remember, we went over this mechanism in dirty detail, right? We went over this in a lot of detail. And so now, if you're looking at this and go, well, what does this have to do with polymers? How am I going to use this to make a polymer? Well, here's the genius, okay? And it's like a piece of art that you look at it and say, well, I could have done that, but it's like, did you think of it? Okay, I look at this reaction and say, I could have done that, but then I'm thinking, well, I didn't come up with it, okay? I didn't invent it. Okay, so you take a dicarboxylic acid like this one here, this is terephthalic acid, and then you just take ethylene glycol, which is abundantly cheap. Well, you can see that you can get a condensation here, sure, okay, so you can form an ester there, but then you can also form an ester on this end and on this end, and so it keeps going, and you guys know what an ester is, so this is a poly, well, the name is up here, why am I writing it again? This is a polyester, right? You all know about, a sweatshirt that's made out of polyester or something. So this is how polyesters are made. Is that cool or what? It's a condensation reaction or a condensation polymer. Why? Because in condensation, we lose a small molecule like water or ammonia or something along those lines. So there you go. So there's your first polyester, which again is just made from a Fischer esterification reaction, and we end up with repeating ester units over and over. Well, you guys know what an amide is, right? We talked about amides at length in chapter 25. Well, if you have a polyamide, another name for a polyamide is a nylon. Okay, you're like, well, of course I've heard of nylon. Everybody's heard of nylon before. So how do you make nylon? It's just a polymer that's held together by amide bonds. Now, there are many different nylons out there, but here's an example of one. This is nylon 6,6, and you can see that it's related to the number of carbons in each monomer. So we have adipic acid. If you remember, oh, my stars go away. This has 1, 2, 3, 4, 5, 6 carbons. And then we have 1,6 hexadiamine, and so there's 6 carbons in each one of these molecules. So when you do the condensation reactions to form the amide bonds here and here and here, between each one of these, you have 1, 2, 3, 4, 5, 6 carbons, right? I pass the nitrogen. 1, 2, 3, 4, 5, 6 carbons, right? So on and so forth. And so we call this a nylon 6,6. Okay, and we're going to see another type of nylon in just a couple of minutes here. So what have we covered in section 27.4 so far? Let's back up just to review in case you've fallen asleep. Okay. In fact, your instructor is not asleep at all, but he is going to take a second here, and he is going to take a drink of coffee. Okay, so we talked about radical polymerization, which involves initiation, propagation, and termination. Then we talked about cationic polymerization, which involves initiation, propagation, and termination. And for cationic polymerization, you want to have an electron donating group on your monomer. And then we talked about why isobutylene polymerizes, but ethylene doesn't, via a cationic addition because a primary carbocation is so unstable. Then we talked about anionic polymerization and how you want to have an electron withdrawing group for that because it stabilizes the carbanion that's formed. We talked about the initiation, propagation, and termination steps. We talked about what a living polymer is. We talked about how an anionic polymerization reaction is analogous to a Michael reaction in that you have a Michael donor and a Michael acceptor. Then we looked at Fischer esterification, and I kind of snuck it in there. Why? Because you have to understand Fischer esterification in order to understand the first type of condensation polymer that we look at, which is a polyester, right? And you can make a polyester, as is shown here, PET, polyethylene terephthalate, which is used in all kinds of plastics. Then I said, well, there's other types of condensation reactions we can have, like a carboxylic acid coming together with an amine to make an amide. And if you have a polyamide, the fancy term we use for that is a nylon. And so we talked about nylon 6,6, and you can have other nylons as well, depending on how many carbons are in your diacid or your diamine. And so now our next type of condensation polymer is a polycarbonate. If you've ever heard of things like Lexan before, okay, it's a really strong polymer. And a polycarbonate is repeating carbonate units. Now, if you're looking at that and going, I'm not sure what a carbonate is, well, you would remember learning about the carbonate ion in General Chemistry 1. So if you take the two oxygens that have negative charges in the carbonate ion and you put R groups on there, you get a carbonate. Okay, so a carbonate in organic chemistry is going to have a structure that looks something like that. There's a carbonate, so don't worry about this. That's an ion. So how do you make a carbonate? Well, carbonates are actually made from phosgene, and phosgene is one of those compounds that annoys students sometimes because they'll say, I always thought why isn't there phosphorus in phosgene? Okay, there isn't. It's this compound here, but you've got a dipole going this way, and this way. What does that mean? It means the carbon in the middle is so electrophilic, it's ready to react with anything. In fact, phosgene was used in chemical warfare because it's such a powerful electrophile. But anyhow, I digress. But you see how you could do two nucleophilic acyl substitutions on phosgene with an alcohol, and then you make a carbonate. So how do you make a polycarbonate? Well, here's how they make Lexan, which I told you is found in things like really strong windshields and things like that. It's made from phosgene and bisphenol A. And anyhow, so you take the phosgene, you react it with bisphenol A, which has two hydroxyl groups, and you end up with Lexan. And I'm not going to go into the whole history of bisphenol A, but I'm sure some of you have heard of BPA plastics, okay? So BPA plastics, there was a whole controversy years ago surrounding Nalgene bottles that contained BPA plastics. Due to there were some conflicting reports on the detrimental effects of BPA, and I'm not going to go into all of that, but I think that now if you buy a Nalgene bottle at REI or something, it will say BPA free. Anyhow, I don't know if any of those reports were substantiated or not, but anyhow, you might find that interesting. Okay, question 27.6 just says determine whether preparation of each of the following compounds or polymers would be best achieved via cationic or anionic. So do we want to make this cationic or anionic? Well, let's think about this. If it's cationic, then we want to have an electron, what? donating group, right, because it's going to stabilize the cation. If we have an anionic polymerization, we want an electron withdrawing group because that helps to stabilize the anion. Well, if I start by looking at this polymer here, how would you categorize a nitrile? Would that be electron, what I have in the black circle, would that be electron donating or electron withdrawing? Anybody? And it's not a loaded question. There's no trick in here or anything. Would a nitrile be electron donating or electron withdrawing? Yeah, exactly. Thanks, Alyssa. It's an electron withdrawing group. That's right. And so this one is going to be best made via anionic addition. What about the next one, the methoxy group? We said it's the oxygen is electron withdrawing via induction, but the lone pairs, if I pencil them in, are electron donating via resonance. And so this is actually an electron donating group, right? If you think of aereo, okay, resonance is going to beat out induction. And so this is an electron donating group. And so this is going to best proceed via cationic addition. And what about the last one, the alkyl groups? Would you say those are electron withdrawing or electron donating? And again, it's not a trick question. Would these be electron withdrawing groups or electron donating groups, methyl groups? Would these be electron withdrawing or electron donating, some methyl groups? These would be electron donating groups, okay? So electron donating groups, they're electron donating via hyperconjugation. All right, and so this compound is going to be best made via cationic radical addition. All right, let's try another one. It says here, draw the polymer that would be generated from the acid catalyzed reaction between oxalic acid and resorcinol. So of course, this is going to be a condensation polymer, right? Because you're going to make an ester. This is going to involve esterification. Okay, so if we have the oxalic acid and then we have the resorcinol, we could start with our oxalic acid, which is going to look something like this, okay? And then we're going to have an ester to our resorcinol. Not my best artwork, but anyhow. So then we have another oxalic acid, and then we have another resorcinol. It looks like this, and then yeah, then we have something that looks like this, and then we'll just kind of close it like that. So that's going to be our repeating polymer that we would get like this. And of course, you could just make a simpler version of this. Okay, all you would have to do is just chop this part out. Okay, just take this part out, go copy and paste it over here. Okay, and then I'll change the color so we don't get confused and say this is the smallest repeating unit, okay, of the polymer is this right here. Okay, give me a thumbs up if you think you could draw the copolymer that's made from the esterification. Cool. All right. Next one says Kevlar is a condensation polymer used in the manufacture of bulletproof vests, and like I said, and canoes. Okay. Identify the monomers that are used for the preparation of Kevlar. Well, you can see that Kevlar is held together. You've got an amide bond here, an amide bond here, an amide bond here. And so you can see the diamine that it's made from is here. And then you can see the dicarboxylic acid would be this portion right here, right? Then you see the diamine again. Then you see the dicarboxylic acid again, like that. So if we wanted to draw the carboxylic, let's do the amine first, I guess. That would be what? It would be this. So we have our 6-membered ring, NH2, NH2. And then here we would have our dicarboxylic acid, which is going to look like that. And there you go. So this one here, this is terephthalic acid. And the one in red, this is called paraphenylene diamine, but the name isn't here nor there. It's just asking you to draw the monomers is all you would need to do. Okay, it says the next one, identify the monomers used to make each of the following condensation polymers. So remember, if it's a condensation polymer, so far we've looked at something that you're going to lose water along the way. And you can see that this one here is a polyester. Right, polyester. Whereas the one below it, right, these are carbonates, excuse me. So this is a polycarbonate. Okay, so for the polyester, we do the polyester first, you can see the dicarboxylic acid is going to come from this part here. So this is malonic acid. And then your diol is going to come from this portion here. So if we draw the diol, you can see that it's ethylene glycol. And the acid is going to be, oops, let me draw it like this. The acid is going to be malonic acid. And there you have it. Those are the two monomers. For the other one, the one below it, if it's a polycarbonate, we know it's made from phosgene. Right? Phosgene is going to be our electrophile, and our nucleophile in this case is going to be this, what would you call it? 2,2-dimethyl 1,3-cyclohexane diol, I guess is what you would call that compound. So we'll scribble that over here. So it's going to look something like this. And there you go. Those are the two monomers that you would use to make the polycarbonate. This is the last question in the chapter. It says nylon 6. Okay, so nylon 6. Notice you have 1, 2, 3, 4, 5, 6 carbons here in epsilon aminocaproic acid. But anyhow, it says nylon 6 is a polyamide used in the manufacture of ropes. It can be prepared via hydrolysis of epsilon caprolactam to form epsilon aminocaproic acid, followed by acid catalyzed polymerization. So draw the structure of nylon 6 and compare it with nylon 6,6. Which one has a smaller repeating unit? Well, you can see here that we have the carboxyl end here, and then we also have the amino end. So if an amino end, all right. So if we have another, we draw another one of that same amino, or same, yeah, it's an amino acid, 1, 2, 3, 4, 5, 6. And then we have the amino group like this, okay? So we're going to get a condensation reaction right here, and then we're going to form an amide. So that's going to be the repeating unit. So if we wanted to draw the polymer, we could just start with something, I mean, we can start it anywhere we want, really. But why don't we start with something like this? So we'll put our carbonyl here, okay? 1, 2, 3. 1, 2, 3, 4, 5, 6. Then we'll have our nitrogen. Then we'll have our amide. So 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Just making sure. Then we have the carbonyl. 1, 2, 3, 4, 5, 6. And then we're going to have something that looks like this. Okay, so I drew it way too long. Okay, you don't have to draw all this. The repeating unit is just this part here. So you see the repeating unit only involves a total of 1, 2, 3, 4, 5, 6, 7 atoms, okay, in the main chain of the repeating unit. But if you go back to nylon 6,6, which I have to go back a few slides, but it's all the way back. Where was it? Jeepers. Where am I? No, that's where. Did I skip it? Did you guys see it? There we go. That's a little better. So in nylon 6,6, you see that our repeating unit is all of this here. Okay, this is our repeating unit here, which is a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms in the repeating unit. So there's your answer right there. So if we go back here, we'll say The one that has the smaller repeating unit is going to be the nylon 6. It's a much smaller repeating unit. It's half the size of the nylon 6.6. All right, and there you go. And that covers all of the content that you need to be aware of for chapter 27. If you want to read the rest of the chapter, it's not very long, but again, it's not tested on the ACS or anything like that. The only part that I think that is important, so we talked about all of these addition polymers that we've covered today, like whether it was radical addition, cationic, or anionic, those are all addition polymers, every single one of them. They all have that in common. And then you can also have what are called step growth polymers if you want to read about those. As far as branching, you can also cover that part. And I'd also add in here that there's a section where it talks about urethane. So urethane, if you've ever heard of urethane or used a urethane-based stain or something like that, you might find that section kind of interesting. But again, you don't need to know that for the quiz or anything like that.